Okay, everybody, what I've done is I've compiled a simple document from this document, chapter 10, refrigeration cycle. This is on the team's file system. Now this goes through how to calculate the COPR. It also goes through the stages of the cycle, the refrigeration cycle. You'll have a copy of this. I don't want to go into every page of this. It's not necessary. I want to go into the calculations. Now, this is what I'm interested in. I'm interested in this question here and how these calculations were derived from this question here. So all I'm going to do, I'm going to go through these questions here. Also, these deviations from this question here. Now the question goes on to the next page, asking to calculate the COPR refrigeration and also COPR Carnot, which are slightly different, okay? But you need to read this and do this yourself because I don't need to go into this too much detail. I'm just going to show you how to get H1, H4, H2 and H1 so you can do all these calculations yourself, okay? Now this is just an example. I'm going to be changing one or two numbers here and there, but the principle is going to be exactly the same. Okay, so what I want to do, I want to begin. Now, I'm going to be going back and forth to different pages, so you might have to stop this video sometimes and then continue. So let me start with this first of all. What we have here is what we've mentioned in class, and there's a PowerPoint I've associated with this as well, so you have all or more than enough information that you need. Okay, now this is the cycle based upon the terminology in the thermodynamics. I'm not going to concentrate on that just at the moment. Okay, I'm going to concentrate just on normal wording so you all understand carefully. Okay, now what you have 4 stages of refrigeration. You've got 1, 2, 3 and 4. Okay, now you've got the evaporator, you've got the compressor, which is the work in, you've got the condenser, and then you've got something called the expansion valve. Sometimes it's known as a throttle. Now, the cycle of a refrigeration system is the same as in steam table. So 2 ways to look at the cycle. One is by using something called the T and S diagram, or temperature and enthalpy diagram. Okay, I should say temperature and entropy diagram. Okay, I get them confused as well. And the other one, which is more commonly used, is by using something called the pH diagram, which is the pressure and enthalpy diagram. I got it correct this time. Okay, so I'm going to be going through this diagram and this diagram here. Remember, these are standard diagrams. Okay, it's standard formats. Sometimes in real life things might be slightly different. Okay, it's not really too much of an issue, but they're important to understand these diagrams. In order to get the calculations you want, you need to get the enthalpy and entropy at each in particular stage. Let me give you an example. If you look at stage 1 to 4, according to the TS diagram, stages 1 to 4, okay, will have the same S, which in this case it's going to have the same entropy. So stages 1, okay, 4 to 1, I should say, they're going to have the same level of S number. That's just an example. So by looking at the diagram here, you can see that the S number from 4 to 1 should be exactly the same. That's just an example. Let's just continue. On the diagram here, it's got an example of a very simple refrigeration system. You've got a freezer compartment and you've got a fridge compartment. Okay, and it goes to some simple equations which we're going to go through. These equations are very important to be able to answer the questions, but I've done it quite comprehensively, and so I think there shouldn't be any issue with following these. Okay, now let me go on to the question. Okay, now read the questions really carefully, and you need to understand the question, the wordings really well. Example 10.1, it's got here a refrigerant 134a. Now there are hundreds of types of refrigerants, to be honest with you, using different chemical formula, and they all have different evaporation, you could say, boiling points or saturation points, and we're using 134a because it's quite common. Okay, R134a is the working fluid in an ideal compression refrigeration cycle, which is an ideal system that we normally use. The refrigerant leaves the evaporator at minus 20 degrees C and has a condenser pressure of 0.9 MPa. The mass flow rate is 3 kilograms per minute. This is really good. This is going to be very important. Find the COP, coefficient of performance, refrigeration, that's why it's got the small r at the end, and COPR, refrigeration Carnot, which is slightly different, okay, for the same T max and T min. And the tons of refrigeration. This is just terminology which will come through in a second, okay? Now you might be thinking, what on earth is all this? Okay, this doesn't make any sense. So I'm going to move away from here and go to my notes. Now what you have here is you have a refrigeration cycle, which I've just mentioned before. Now the first stage, I'm going to try to use a finger. I've got small fat fingers. I need to use my pencil. Okay, you've got the evaporator, you've got the compressor, you've got the condenser, and then you've got the expansion valve, sometimes called throttle. They are slightly different, but they do the same thing more or less, okay? But for this case, just keep it as the same. Now what you've got something called work in, the input into the system. Now remember, a refrigeration defines the second law third of thermodynamics, because you try to get cold energy transferred to hot energy, or cold place to a hot place. Now that's not really physically possible, and so you need some kind of work energy for this to happen, some kind of a pump or a machine based device. So in this case we have a compressor, and that's the device that makes a lot of noise in refrigeration, the motor type of sound. Okay, now that's energy in, that's electricity, it's energy, it's joules, it's coming into the system to allow cold QL, cold energy, to go to QH, which is the condenser, which is the hot energy here. Okay, so this transfers the energy from here, go into there, then it's released back into here, the liquid, and the cycle starts again and over again. That's all that's happening, nothing else. Okay, now let me go for a different example here. This is what we normally do in classroom. You've got your QL. Now Q is heat energy, so this is cold energy being transferred to hot energy. That it can't happen by itself, so what you need some kind of a pressure, which is called W in, or work in. It's going from here to there. Okay, TL, this is for the Carnot cycle. TL is the temperature low, and TH is temperature high. TL and TH. Okay, you might need to do a bit more research in terms of how this works in more detail, but I'm going to try and see what I can do my best. Okay, I'll give you about 10 seconds just to think what I've just done so far. Okay, I'll continue now. Okay, that was less than 10. Now, so what you've got here is you've got liquid coming into the system. It doesn't detail here where the liquid goes into the system. That isn't necessary. Okay, but what you've got liquid coming into the system, and the liquid is compressed. When it's compressed in the compressor, what happens is the pressure increases. As the pressure increases, this is a law of thermodynamics as well, temperature increases. So the liquid's coming into here, it's being compressed, it's being squashed into here, squashed. High pressure, high temperature. Okay, now the high pressure liquid going along here is going into the condenser. It must be cooled down before it goes back into the system. So you know the wiring at the back of the refrigeration system, the copper tube wiring, that's the condenser. So as the liquid goes from here to here, it's really hot, so it needs to cool down. Cool. And then what happens when it's cooled down? Okay, it goes to the expansion valve. Now the expansion valve, what does the expansion valve do? If you look here, 3 to 4, it reduces the temperature 3 to 4. Because you see temperature, it reduces the temperature. The way it does that is by it reduces the pressure. The expansion valve reduces the pressure and reduces the temperature. As it does that, you get cold, very low, you get hot liquid here and you get cold liquid here. Okay, the cold liquid goes out of here, goes into the evaporation system, which goes inside the refrigeration. Now that picks up heat because it's cold going in here, but the heat from the food inside the refrigeration is picked up by the liquid. So the liquid actually gets warmer and warmer and warmer and warmer until it gets to here. Okay. Now, when it gets to here, a stage happens. Let's find out what happens here. So when let's see what happens between 4 and 1 first of all. Go to here, 4 and 1. Now the entropy actually increases quite substantially, which is disorder. Okay, if you go to this diagram here, the 4 and 1, the enthalpy increases as well. As you can see, the entropy and the enthalpy increases as well between 4 and 1. Now from there, it needs to go to 1 to 2. What happens between 1 to 2? 1 to 2, because energy is compressed, or the liquid's compressed, as you can see, 1 to 2, temperature increases substantially between 1 to 2 as pressure increases. Now if you look carefully, it's not really proportional because the pressure increases from here to here, but it's quite exponential it's not really linear, it's actually slightly exponential. If you look here, it goes straight up. So it's not 100% proportion, but more or less it does the same action. Okay, now I want to go to here and explain this in more detail here. Okay, now in the booklet that you've got, if you go back to the booklet, this one here, it actually tells you what happens at each and every single stage here on this page here. It tells you what happens at each and every single stage. You just got to read the wording carefully, but I've put everything in here for you. Now let's go to here now. Now you've got the evaporator, okay, H1. These are your stages 1, 2, 3, and 4. So I've labeled them as H1, H2, H3, and H4, the enthalpy. Okay. Now you've got something called saturated vapor. Okay, saturated vapor is basically it's where X equals 1. It's pure. It's pure vapor. There's hardly any liquid inside. Okay, that needs to be condensed. Okay, when you condense vapor, you get it back into some kind of liquid form. Okay, so when that goes from here to here, it gets compressed. Okay, now as you compress it here, you're going to create something called superheat. It becomes extremely hot, becomes superheated, and you need to look at superheated tables for this. The separate table from these tables here. Just remember what I just said there is very important. Okay, it gets really superheated. Okay, now then when you've got from here, then it gets cooled along here. It goes back into liquid form by the time it gets to here. Okay, the temperature decreases substantially by the expansion valve because it's still quite hot by the time it gets to here. It gets decreased substantially. That low temperature cools the refrigeration system. Okay, it gets slightly hot, that low temperature. Okay, becomes saturated vapor because there it's a liquid. Okay, saturated liquid vapor. That's where X equals 0.3, 0.4. Doesn't, it's a bit of a mixture, and it's not pure. It's not pure liquid, not pure gas. It's a mixture of both. Then it goes through here. Then it becomes pure vapor. Now, when it goes through vapor, it goes back into the condenser, and it goes into the system constantly. As long as there's some kind of work in. The work in this case, according to the question given to you, is 900 kPa, which is 0.9 MPa. at 3 kilograms per minute, which is the flow rate per minute, 3 kilograms per minute. Very important. Okay, so according to the booklets, go back to the booklet. I hope you're able to follow me actually. Now, according to the booklet, you've got stage 1, stage 2, stage 3, stage 4. Okay, now these numbers they come about by the following way. Now, I'm going to try and go slow here because it can get a bit tricky. Okay, here we go. Now let's look at stage 1. Okay, stage 1, the compressor inlet. So stage 1 is there. Okay, where it's got number 1. I'll show you now. Number 1, compressor inlet. Stage 1. Go back to here. There, compressor inlet. And it's the same, obviously, in all the diagrams here. Stage 1, stage 1. Okay. Stage 1, we know the temperature is minus 20 degrees because that's what the question says. Why do we know it's minus 20 degrees? Okay, why do we say it's minus 20 degrees? Because the question says, from what I understand, the question says the temperature. If we go back to the temperature on the inlet of the evaporator is minus 20, so therefore the outlet's going to be the same. The temperatures increase or decrease as it goes along here. Okay, so temperature compressor inlet, oh yeah, is minus 20 degrees. Now X is 1.0, which means it's a pure vapor. Okay, a saturated pure vapor. There's no liquid inside here at this particular stage. So the compressor at stage 1, it says there as well, it's X equals 1. It's very important to know this, okay? And that comes from the diagrams. I'm going to show you. I'll turn this over. I'm going to show you the diagram, okay? Now, if you remember this diagram in class, that's X equals 0 is there. That's liquid format. When it becomes dry, X equals 1, okay? So the lower the number, the more pure X is it's going to be. If it's X equals 0, which is around here, that means it's going to be basically just liquid, saturated liquid, then liquid, then vapor, mixed, then it goes into pure vapor here. Okay, very important you understand that concept. So that's how you get stage 1. Okay, now how do you get these two numbers here? This is the interesting part. This is where you look at these. You've got this as well in your notes. You've got the table for the saturated refrigerant 134a. You've got the temperature table. Okay, now we'll look at minus 20 degrees. Look across, because it's pure vapor. We're going to look for H, saturated vapor. That's saturated liquid, that's saturated vapor. So if you look here, it's 235.31. If you make your way across, that's what H is at that particular, the enthalpy at that particular time, or instant I should say. Okay, so it's 2. Now S equals 0.332. That's the same, because that's just what we've just done now. Find my pencil. Go across 0.9332. Saturated vapor. Okay, there you go. Okay, and that's going to be entropy. Okay, and that's your enthalpy, which is there. Okay, that's energy per kilogram. It's quite high, and that's going to be your the disorder. The disorder is going to be quite high because it's vapor. Vapor always has high disorder compared to a solid. Okay, now let's go to stage 2. Stage 2 says it's a superheated stage. That's when it's come out the compressor is extremely hot, because it says their compressor exit. Okay, now you've got to see the superheated tables. Okay, now P2 equals 900 kPa. Okay, now we know this because P2 is where? P2 is the pressure of the compressor, which is just here. Okay, so it's going to be 900 kPa. That's what the question says as well. It's 900 kPa. Okay, now S2 equals S1. Okay, so the entropy at S2 equals S1. How do we know this? If you look at the entropy diagram here, S the S2 and S1 are the same. The entropy S, the temperature changes, but the entropy stays the same. Okay, so if you go back to here, okay, so we've got stage 2 S, and that's 0.9332, which is from over here. Okay, now H2 roughly equals 275. Why have I got that? Well, I turn the table over, this table here. That's the normal values. This is a superheated value, and it tells you there, superheated refrigerant. Okay, these numbers are not an exact science, by the way. The question in the booklet gets it exact to the decimal point. I'm not sure where they've got this from. Okay, but let's have a look. Let's have a go at this. On here, you've got very smaller tables combined together. Look for your pressure, 0.9. Okay. That's a normal. That's a saturated temperature. That's a normal saturated temperature. But then you've got to look at these because it's superheated. You're looking at the superheated temperatures here. Okay. Now what you've got is, if I remember correctly, it's S1 S2 equals 0.9332. So 0.93 it lies between these two. If you go across, it's between 40 and 50 degrees centigrade. Now if you go on here, I've put here roughly 44 degrees C. Okay, so this is from the TS diagram entropy at S1 equals S2. Okay, so this is the superheated table. Now let's go on to S3. S3 is a condenser exit. Okay, now at this point the temperature should obviously be should have reduced. If the temperature is reduced, all the vapor should have disappeared. If it disappeared, it's gone into a pure liquid form. So that's why you've got here saturated liquid, and X equals 0.0 because it's going to be pure liquid. Okay, we know what the pressure is. P3 equals P2. Okay, and if you look here back onto the pressure table, pressure P2 equals P3. P2 equals P3. Okay, it's exactly the same. But here, it's just that the liquid is more going to be like a liquid form because it's very hot. It's all vapor because it's very hot. Then it cools as it goes along the piping, the back of the refrigerator. Then it becomes a liquid by the time it gets to here. Okay, but it's still very hot, by the way. Okay, it's still really, really hot. We need to reduce because it's a coolant, so we need the hot liquid here to still cool whatever is inside the refrigeration system. So anyway, so what we've got here, we've got this, and then we go back here. Now H3 roughly equals 100 H. Okay, well, why is that? Where did I get that from? I got it back onto the. If you go back onto the tables, the normal tables, not the superheated table, but the normal one. Okay, because it's gone away from the superheated temperatures now. What we've got here is what have we got? 900 kPa. Now, if you look here, if you look at the pressure column, go to 900 kPa, which is roughly around 0.9 MPa, which is roughly around here, 0.900. It's around here. If you go to here, see what I've done? Because it's saturated liquid, it's the enthalpy at saturated liquid, which is 100, roughly 100. So I've put here roughly the enthalpy at that's because it's saturated liquid. The enthalpy is going to be 100, and the S is going to be 0.385. Because it's liquid, the disorder, the entropy is going to be a bit lower. Okay, if you look there, the entropy is just a tiny bit lower. Okay, I've just put here roughly. Okay, I've not made it an exact science. Okay, where am I now? I forgot where I am. Okay, there. See normal table, saturated liquid column. So that's why I've got these two. So we've got H1. We've got H2, we've got H3. How do we get H4? Now H4 is, if you go back onto the tables here, H3 and H4, we'll use this table here. Where's my pencil? Okay, H3 and H4 are the same, only the pressure drops. Okay, so H3 equals H4, and H3 equals H4, which is roughly 100 H. Okay, now because at this stage, if you look carefully what I've the reading here, compressor exit, saturated no, I'm not, sorry, I do apologize, I'm here actually, the throttle exit. Now the throttle exit, it's saturated liquid vapor. Okay, if it's saturated liquid vapor, that means the X isn't going to be 0 and it's not going to be 1. Okay, it's going to be a mixture of liquid and vapor, so X is going to be X point 0 point something, X equals 0 point something. Okay, now I've got X equals 0.39. Now where did I get X equals 0.39? I mean, where did I get that? Okay, now the way I got it was it's a bit of a calculated guess. If you go back and you've got this as well. Okay, this is a very important chart to refer to. Okay, now if you look here, so if we go back into, I do apologize, go back into here, H equals 100, roughly 100, temperature's minus 20, minus 20 is there, H is 100, which is there. If you go down, it says 40%. It says X equals 40% at that stage, but it's not quite that. It's zero. It's a bit less than that. So I've got 0.39. It's something. It doesn't really matter what you put, as long as it's roughly what you've got. Okay, it doesn't really matter. Okay, so that's why I've got that, because these are the X values here. X 0, 10%, 20%. This is the percentage of how pure they are. The 100% is pure vapor, which X equals 1.0. Okay, that's how I've got this. So you can use, so that's why you've got to really use charts and tables. And to be honest with you, there's an easy way of doing everything, and that's by using a program on the internet where you can put in numbers and it gives you all the calculations. But this is just a skill for you to learn. Okay, now, so any questions, you could come and see me or ask me. We just go back into here for a second. If you just want to bear with me, it's up to you. Okay, sorry. Go back into here. These are very important notes which you need to learn and read. Okay, now you've got QH equals mass flow rate, H2 minus H. Remember, m dot is mass flow rate, and in the question it's 3 kilograms per minute. Okay, it tells you there 3 kilograms per minute. 3 kilograms per minute. That's the mass flow rate. That's m dot. Okay, and you should be able to work out the rest of these by your COPR. Now, COPR is actually the actual COP for the actual refrigeration system. You need to also learn about what is more about COP, maybe in your research, in your question, in your assignment, even though it's in the PowerPoint and I've talked about it this time. Learn about the definology. Now, Carnot is not a real refrigeration system, and it's an ideal one. And one of the questions asks you the difference between this and this. Okay, and that's quite simple research actually. So anyway, so good luck. Take care. Bye.